special relativity theory, derivation of length contraction. Looking at keywords or key statements. 1. Frame of reference is the coordinates that describe the position of an object, set of coordinates, space, and time coordinates. The space coordinates are x, y, z, and the time coordinate is t. Number 2, inertial frame of reference. It obeys Newton's first law. Objects won't accelerate unless they are acted on by external force. Stationary and constant velocity. This is what it means, that an object in a stationary state will continue to be in that state, or at a constant velocity will continue to be in that velocity. No acceleration. Number 3, inertial. Inertia is a property of matter by which it remains at rest or at uniform motion in a straight line unless acted upon by an external force. The inertial mass of an object is its tendency to resist changes in velocity. Number 4, Einstein's theory of special relativity only works in inertial frames and is based on 2 postulates, which means assumptions. The first one, the laws of physics is the same in all inertial frames. Second, speed of light in free space, that is vacuum, is invariant. Invariant means same or constant for all inertial observers or sources. If you have 2 frame of reference, S and S prime, where X is parallel to X prime, Y is parallel to Y prime, and Z is parallel to Z prime. Both frame of reference are starting from the same point, 0 and 0 prime. The observer B has a rod AB, and the frame of reference S prime will move off with a velocity of V, while the frame of reference S will stay at rest. Now, this is the frame of reference S at rest, and the S prime with a velocity V. The S prime is moving with a constant velocity, so it will have the coordinate, space coordinate of X prime, Y prime, Z prime, and T prime, and there's a time coordinate. The rod has a length of AB, which is to be measured. We're going to measure the length of AB from the stationary frame of reference observer A and measure the length of AB with observer B in the same frame of reference. Using Lorentz transformation for S prime and S, we're going to write the Lorentz transformation for S is going to be x equals to gamma, open bracket, x prime plus vt prime, close bracket. And then we have y equals to y prime, z equals to z prime, and t equals to gamma, open bracket, t prime plus x prime v over c squared, close bracket. For S prime, we have x prime equals gamma, open bracket, x minus vt, close bracket. Y prime equals y, z prime equals z, and t prime equals gamma, open bracket, t minus xv over c squared, close bracket. So looking at the stationary observer, to measure the length, what the observer will see will be xb minus xa, and that's delta L. And that delta L is referred to as relativistic length because that is relative to the observer A. For S prime, xb prime minus xa prime equals delta L naught, and that is called proper length or rest length because that rod is measured in the same frame of reference as the observer B or the S prime frame of reference. So that would be proper length seen by observer B, but the length seen by observer A will be relativistic length. Using the Lorentz transformation, x prime equals to gamma, open bracket, x minus vt, close bracket, xb prime equals to gamma, open bracket, xb minus vtb, close bracket. Xa prime equals to gamma, open bracket, xa minus vta. If we take away xa prime from xb prime, we get xb prime minus xa prime equals to gamma, open bracket, xb minus xa minus v, common factor here is v, open bracket, tb minus ta, close bracket, close square bracket. But remember that ta has to be equal to tb because if the frame of reference S is measuring the ruler, it has to measure the ruler at the same time, and therefore the TA has to be equal to TB. The delta L naught is XB prime minus XA prime, which is equal to gamma delta L. Delta L is XB minus XA, and this will be 0 because TA is equal to TB, therefore TB minus TA will be 0. So that will be 0. Now we're going to get delta L will be equal to delta L naught, the original length, the proper length, over gamma. But 1 over gamma is, this is 1 over gamma, 1 over 1 over root 1 minus v squared over c squared. And that will be equal to root 1 minus v squared over c squared. You can see delta L equals to delta L naught, that one, times 1 over gamma. And that's 1 over gamma here, which means delta L will be equal to delta L naught root 1 minus v squared over c squared. And that is the distance contraction, because the root of 1 minus v squared over c squared will be less than 1. And if you times that by the original length, the proper length, this will be smaller. So we call that length contraction. Example 1. What is the length contraction of 10% speed of light? So 10% of speed of light is 10 over 100 c is the speed of light, and that equals 0.1 c. Therefore, delta L, which is the relativistic length, is equal to delta L naught, the proper length, times root 1 minus v squared over c squared. And v is equal to 0.1 c. So if I substitute 0.1 c here, we get this. So that's 0.1 c squared. And then delta L equals to delta L naught root 1 minus 0.1 squared, because the c squared cancel out. And then delta L, which is relativistic length, equals to delta L naught times root 1 minus 0.01. Delta L is equal to delta L naught root 0.99. Therefore, delta L is equal to 0.995 delta L naught. At 10% speed of light, the relativistic length is just 0.995 times delta L naught. That's a small difference. What about at 90% speed of light? Question number 2. What is the length contraction of 90% speed of light? As you can see, 90% is closer to speed of light than 10% speed of light. So V is equal to 90 over 100 C. That equals 0.9 C. Again, we write down the length contraction equation. Delta L, relativistic length, is equal to delta L naught, proper length, times root 1 minus V squared over C squared. Substitute V equals 0.9 C into the equation. Then we get delta L naught times root 1 minus 0.9 squared. And that gives you delta L naught times root 1 minus 0.81, which then gives you delta L naught times root 0.19, and that delta L equals to 0.44 times delta L naught. That is a drastic reduction, more than 50%, and that's because it's closer to the speed of light. You get more length contraction when you're close to speed of light. This is the graph relationship where you got the relativistic length over proper length on the y-axis, and you got the speed over the speed of light. So if you go from 0 to 1 here and 0 to 1, this decreases and then sharply decrease over here. And so this is the relationship between the two ratios of speed and length, where L is relativistic length, L naught is proper length, V is the speed of S prime, and C is the velocity of light.